Dear students, Assalamu alaikum. Welcome to lecture of econometrics. In this lecture, we will discuss the multiple regression model. We discussed before this lecture the simple linear regression model. We conducted tests of significance, and we also discussed in detail the coefficient of multiple determination as R square as goodness of fit, and we also discussed some of the numerical questions derived to the simple linear regression model. Just like the simple linear regression model, the material used in this lecture has also been taken from the Collinearity's book Theory of Econometrics and Introductory Exposition of Econometric Methods. Dear students, we have studied in the simple linear regression model that we have two variables, one dependent and one independent variable. And that is the reason that that model is also known as two variable model, in which y is the dependent variable and x is independent variable. If we write it in functional form, we can write y as a function of x. Suppose we take an example of the law of demand. We can say that demand is a function of price. Here demand and price are two variables, where demand is dependent variable while price is independent variable. So it becomes the case of a simple linear regression model. But we often see in our daily life that there are more than one explanatory variables. The demand is affected by not only by the price of the product, but there are a number of other determinants as well. So in this case, if we take another example, determinant of demand, consumer income, then demand becomes function of the price and consumer income. As we have more than one explanatory variable, here we have two explanatory variables, which can be symbolically write y is a function of x1 and x2, where y shows the demand and the x1 shows price and x2 shows the consumer income. In this case, we cannot use the simple linear regression model because here we have more than one explanatory variable. So we use the multiple regression model. Multiple regression is the extension of simple linear regression, where we have more than one independent variable, and we can discuss the cases of the multiple regression model is given below. First, we take the sales function. We know that the sales of a firm depends on the price of that product and the advertisement expenditure made on the advertisement of that product. So if we write, we can write mathematically y as a function of x1 and x2, where x1 shows price and x2 shows the advertisement expenditure and y shows the sales. So it becomes the multiple case for multiple regression model. Similarly, we can say output of a land depends on seeds and fertility of land, where x1 shows seeds and x2 shows fertility of land. We can write the general form of multiple regression model with two variables is by adding this b2 x2, we can write the two variable multiple regression line as y is equal to b0 plus b1 x1 plus b2 x2. It is the mathematical form of this model. But we know that there are other factors as well which can affect the dependent variable. In order to cover up all those missing observations, we can add the stochastic term or the random term. So the complete equation multiple regression model with two explanatory variable becomes y is equal to b0 plus b1 x1 plus b2 x2 plus ui. Dear students, this equation consists of two parts. One part is this one, b0 plus b1 x1 plus b2 x2. This part is called systematic component or systematic part, and ui is a random term or the random component of this model. Dear students, just like the simple linear regression model, the multiple regression model has also few assumptions which if not fulfilled, we will have the problems in the results. For example, first assumption is UI is a random variable. Just we discussed in the simple linear regression model, UI is a random variable, which means that the value of UI is by chance. It can be negative or positive, or it can be 0. The second assumption is the mean value of UI in any particular period is 0, or expected value of UI is 0. Similarly, assumption number 3 is the variance of UI remains constant in each period. Symbolically, we can write mathematically expected value of UI square is equal to sigma square U, which is a constant. And this assumption is known as the assumption of homoscedasticity. Here has some spelling mistake. Homoscedasticity, which means that the variance is constant. If this assumption is violated, which often happens in econometrics, if this assumption is violated, means if the variance of the UI is not equal to sigma square U, then this becomes case of the heteroscedasticity. And in case of heteroscedasticity, we can face so many econometric problems. Assumption number 4 is UI has normal distribution. UI is normally distributed with 0 mean and sigma square variance. Similarly, assumption number 5 is the random terms of different observations. UI, UJ are independent. The values of UI corresponding to X are independent from the values of any other UI corresponding to XJ. If you have different observations, then the random terms of different observations are independent. If this assumption is violated, then we can face the problem of autocorrelation. And one of the causes of the autocorrelation is the misspecification of the model discussed in detail in lecture number 2. Similarly, dear students, the assumption number 6 of the multiple regression model is UI is independent of externality variables. UI has, for example, we take this case, this UI is independent of x1 and x2. And assumption number 7, also a very important assumption, that the externality variables are not perfectly linearly correlated. In this case, we have two externality variables, x1 and x2. The assumption shows, this assumption number 7 says that x1 and x2 are independent. They have no relationship. If this assumption is violated, means if x1 and x2 are found correlated, then we will have a problem known as the problem of multi-collinearity. The problem of multi-collinearity will be discussed in the coming lectures. Assumption number 8 is externality variables are measured without error. This similarly, the model assumes that you have not made any error in adding the in measurement of these explanatory variables, because sometimes the variables are captured by proxies. So be sure that you have used appropriate proxy for measuring the variable. Similarly, assumption number 9 is macro variables should be correctly aggregated. You know that often the macro variables are the summation of the micro variables, or there are different methods of the calculation of the macro variables. For example, if you take the GDP, we know that GDP is measured by different methods known as the product method, expenditure method, the value add method, the income method. So be sure that the method you have used has calculated the GDP in proper way. Similarly, the calculation of inflation is also done through different price indices. So be sure that you have used the proper method to find the exact value. The relationship being estimated is identified means that the equation which you have written is in unique unique mathematical form. And the assumption number last one is the relationship is being correctly specified, means that you have made no mistake in the specification of the model, and you have included the right variables in the dependent and independent position. So continuing the lecture, dear students, we come to the estimates of parameter. You know that in case of the multiple regression, we have more than two parameters. You see here on your screen the multiple regression model. You see that y is equal to b0 plus b1 x1 plus b2 x2 plus ui. It is a simple multiple regression model with two explanatory variables x1 and x2. Dear students, if you take its estimated form, it becomes y hat is equal to b0 hat plus b1 hat x1i plus b2 hat x2i. By the estimates of parameters, now we are interested in finding the estimates of b0 hat, b1 hat and b2 hat. These are the parameters of multiple regression model with two explanatory variables. So for the derivation of these three parameters, we use the same formula, the same method which we use in case of simple linear regression model. You may remember the case of the ordinary least square method which we use for derivation of estimates in a simple linear regression model. So that method requires the sum of square of residuals. So dear students, the residual, we represent residual by EI, which is actually the difference between the actual value and the estimated value. So look at the screen. We see EI is yi minus y hat, so it is residual. If you take the square of the EI, we also take square on the right hand side, so it becomes square of residual. If we take the sum, we take the sum on both sides, it becomes the sum of square of residual. The sum of square of residual. Proceeding the calculation, we can write the sum of y minus, we know that this y hat is equal to this, you see this equation, y hat is equal to b0 hat plus b1 hat x1i plus b2 hat x2i. So putting the values of the y hat in this equation, we get summation yi minus b0 hat minus b1 hat summation x1 b1 hat x1i minus b2 hat x2i whole square. We can obtain the normal equations by minimizing the sum of square of residual and taking partial derivatives with respect to the parameters estimate b0 hat, b1 hat and b2 hat. We get these equation. You know that the method of the ordinary square requires to minimize the sum of square of residual. So we take the partial derivative and we equate it to 0. So taking the derivative first with respect to b0 hat, we do write the sum of y minus b0 hat minus b1 hat x1i minus b2 hat x2i whole square and equate it to 0. Dear student, then we proceed and take the same partial derivative with respect to the other parameter b1 hat and we get this equation. Then we proceed and take the partial derivative with respect to b2 hat. Then we get this equation and we equate all of these to 0. You know that when we take the partial derivative with respect to b0 hat and solve this equation number 1, we get this normal equation 1. By simplifying the equation number 2, we get the normal equation 2, and by simplifying the third partial derivative, we get the third normal equation. So these are the three normal equations in case of the multiple regression model with two explanatory variables x1 and x2. You remember that we derived two normal equations in case of simple linear regression model. So by solving these equations just we solved in the case of a linear regression model, we can get the formulas for the calculation of b0 hat, b1 hat, and b2 hat. But in case of the capital Xi's, we will get two lengthy formulas which will be very difficult for the students to use and to calculate the estimates. So we process these equations and use the deviated form. So after taking the normal equations through deviated form and solving those normal equations, we can get the parameters estimate given in these three formulas. We can get for the b0 hat as y bar minus b1 hat x1 bar minus b2 hat x2 bar. This will be the formula or estimate for b0 hat. Similarly, for b1 hat, we will have summation x1y, summation x2 square minus summation x2y, summation x1 x2 divided by summation x1 square, summation x2 square minus summation x1 x2 whole square. Similarly, the formula for b2 hat will be summation x2y, summation x1 square minus summation x1y, summation x1 x2 divided by summation x1 square, summation x2 square minus summation x1 x2 whole square. So dear students, these are the three formulas which we derived from the normal equations in deviated form. So we can solve a number of the questions, a number of problems with the help of these formulas. For example, let me solve an equation, an example. This is a table is given and you have been asked to fit a multiple regression line. So this multiple regression line, you are asked to fit this regression line y is equal to b0 plus b1 x1 plus b2 x2 plus ui. These are the values of n, number of observations 1 to 10. These are the observations of the quantity demanded of y denoted by y. These are the observations of the x1 which shows price. These are the observations of x2 shows income. So you have been asked to fit the multiple regression line. So this means that when we fit the multiple regression, this line, the estimated form of this line is y hat is equal to b0 hat plus b1 hat x1i plus b2 hat x2i. So students, for the estimation of b0, we will use this formula by bar minus b1 hat x1 bar minus b2 hat x2 bar. Similarly, to estimate the b1 hat, we will use the formula summation x1y into summation x2 square minus summation x2y into summation x1 x2 divided by summation x1 square into summation x2 square minus summation x1 x2 whole square. This will be the formula for b1 hat. The formula for b2 hat will be summation x2y into summation x1 square minus summation x1y into summation x1 x2 divided by summation x1 square into x2 square minus summation x1 x2 whole square. These are the two formulas which will be used for the estimation of the parameters. Dear students, I wrote the formulas in the beginning of this solution because through which we will come to know what kind of calculations we have to make. We will need y bar, and you know that y bar is equal to summation of y by n. Similarly, we will need x1 bar, which is summation x1 by n, and x2 bar summation x2 by n. We will need the deviated forms of the x, small x1 and small y1. Similarly, we will need summation small x1 square, summation small x2 square. We will need summation x1y, so we will need summation x2y and summation x1 x2. For all these calculations, we make the relevant columns from this table. So we first calculate the small y, small x, small x2, x1, small x2. But before going that, we find the means. In order to find the mean of the y bar, we will have to add all the observations of capital Y. When we add them, we get 100. And the number of observation is 10. We know that y bar is equal to summation y by n. So 800 divided by 10, we get y bar is 80. Similarly, summation for finding the x1 bar, we add all the observations of x1. If we add 5, 7, 6, 6, 8, 7, 5, 4, 3, 9, we get 60. And if we divide the 60 by the number of observations 10, we get x1 bar. Similarly, for finding the x2 bar, we add all the observations given in the column of x2, capital X2. We get 8000. It becomes summation capital X2. In order to find the average x1, x2 bar, we divide summation x2 by n. So summation x2 is 8000. 8000 by 10, we get 800. So dear student, y bar is 80, x1 bar is 6, and x2 bar is 800. From these bars, we will calculate the columns for deviated y, x, and the x2. So first of all, if we calculate the y, small y, that will be y minus y bar. We know that y bar is 80, so we subtract 80 from each observations given in the column for y. So 100 minus 80, it becomes 20. 75 minus 80 minus 5. 80 minus 80 is 0. 70 minus 80 minus 10. 50 minus 80 minus 30. 65 minus 80 minus 15. 90 minus 80 10. 100 minus 80 20. 110 minus 80 minus 30, and 60 minus 80 minus 20. So it becomes the column for small y. Similarly, we can construct column for small x1, deviated x1, and it is equal to x1 minus x1 bar. We have calculated x1 bar, which is 6. So x1I minus x1 bar means to subtract x1 bar from each observation in the column x1. x1 bar is 6, so 5 minus 6 minus 1. 7 minus 6, 1. 6 minus 6, 0. 6 minus 6, 0. 8 minus 6, 2. 7 minus 6, 1. 5 minus 6 minus 1. 4 minus 6 minus 2. 3 minus 6 minus 3. 9 minus 6, 3. So it becomes the column of small x1. After constructing the column for x1, we proceed and find the column for small x2, which is x2 minus x2 bar. In this case, we will subtract the x2 bar, which is 800, from each observation given in the column for income x2. So subtracting the 800 from the first observation, we get 200. When we subtract it from 600, it is minus 200. 1200 minus 800, 400, and so on. So it becomes the column of small x2. Dear students, in our formulas, we need in these formulas we need x1 square, x2 square. So we construct the column for x1 square, which is actually the square of small x1. Minus 1 square, 1. 1 square, 1. 0 square, 0. 0 square, 0. 2 square, 4. 1 square, 1. Minus 1 square, 1. Minus 2 square, 4. Minus 3 square, 9. 3 square, 9. So it becomes the column for x1 square. Similarly, for the column of x2 square, we take the square of the column of small x2. 200 is, if the 200 is squared, we get 40,000. Minus 200 is squared, we get 40,000. If we take the square of the 400, 1,60,000, and the square of the minus 300 is 90,000, and so on. Similarly, next step is to construct column for the x1y. So what we do for the x1y, that in this way we calculate the columns x1, x2y, and x1, x2 as well. At the end, we take the sum of the columns constructed for the deviated values of x1, x2. So when we add the small y, we get 3 4 summation y square, so 3450. The summation of x1 square will be 30. The sum of x2 square will be 1580 300 3 zeros. For summation x1 y will be minus 300 and summation x2 y will be 65,000. And similarly, if we sum all the observations in the column small x1 x2, which is actually the multiplication of the column of x1 x2, we will get minus 5,900. If you put all these values in the formulas given in this slide, we get the estimates for b1 hat, as we know that b1 hat is equal to, formula is summation x1y into summation x2 square. So summation x1y is minus 300 and summation x2, this summation x1y is minus 300 into, this is the other observations. We put the observation and calculate them, we get the value of beta 1 hat as minus 7.1882. You can calculate, multiply these and subtract. After making subtraction and multiplication, taking squares, you can get the value of beta 1 hat as minus 7.1882. Similarly, if we put the values in this table in formula number 3, this b2 hat, we can get the estimator for beta 2 hat as 0.0143. And if you put all these values in the formula for b0 hat, y bar, we know that it is 80 minus b1 hat is minus 7.19, x2 bar is 6, minus b2 hat is minus 0.0143 into x2 bar is 800. So by multiplication and solving, we get the beta 2 hat as b0 hat as 111.69. So putting the values of b0, b1 and b2 in the estimated regression line, this let me magnify it. By putting in this equation, we know that b0 hat is 111.69, where plus b1 hat is minus 7.118, so 7.11188 minus into plus minus 7.11188 to x1 plus the value of beta 2 hat is 0.0143. So this becomes the estimated regression line. Dear students, we see here that the sign of the coefficient of the x1 b1 hat is negative, which means that the price negatively affects the quantity demanded, and the sign of the x2, which shows income, is positive, which shows that the income of consumer positively affects the demand for a commodity. After discussing the derivation of the coefficient of multiple regression line, the next topic is coefficient of how to calculate the coefficient of multiple determination. The calculation of coefficient of multiple determination is important because it tells us the variation in the dependent variable y, which is caused by the explanative variables x1 and x2 in this case. So the coefficient of multiple determination, it is usually nowadays, softwares are used in the EViews, in the strata, or whatever whichever software we use. You will get the by default value of the r square. So this part of lecture shows how this r square is calculated. In the two variable case, we discussed that r square measures the goodness of fit of regression equation. It gives the proportion or percentage of total variation in the dependent variable y, which is explained by the independent variable x. The notation of R square can be easily extended to the regression models containing more than two variables. We can extend the R square, the value of the correlation coefficient, to the multiple regression where we have more than one explanatory variables x1 and x2. Thus, in three variable model, we would like to know the proportion of variation in dependent variable y explained by the independent variable. We can write variation in the dependent variable y explained by the variation in the independent variable x1 and x2 jointly. The quantity that gives this information is known as the coefficient of multi-determination, and it is denoted by R square. The correlation coefficient, the square of correlation coefficient in case of multiple regression is, that it is known as the multiple coefficient of multiple determination, and this coefficient of multiple determination shows a percentage change in the dependent variable y, which is caused by independent variables x1 and x2. So dear students, this R square is equal to summation y hat square by summation y square. Remember that this small y shows the small y, which is deviated value of y hat. We know that y hat is the difference between actual and estimated. This y hat can be calculated by y hat minus y bar. Similarly, the summation y square, we calculated y minus y bar, small y. By simplification, we can write 1 minus summation ei square by summation y square, and by taking the LCM we get the summation y square. If summation y square is LCM, so 1 summation y square by 1 equal to summation y square, and summation y square into 1 summation y square, then minus summation y square by summation y square 1 into summation ei square, summation ei square. So now, in order to derive formula for the R square, we need to expand this summation ei square. We know that ei is equal to y minus y hat, which is the difference between actual and estimated value. So, and this y hat is equal to b1 hat x1i plus b2 hat x2i. So putting the value of this small y hat in the ei, we can get the value of the ei. So we can write summation ei square equal to summation ei into summation ei. So we have summation we have y minus y hat instead of summation ei. Because we know that ei is equal to y minus y hat. By putting the value of y hat here, we can get some y minus b1 hat x1i minus b2 hat x2i, and by multiplication of summation ei with this whole equation, we get summation ei yi minus b1 hat summation ei xi minus b2 hat summation ei x2i. Now econometrically it has been proved that summation ei x1i and summation ei x2i, these are equal to 0, so summation ei square becomes equal to summation ey. We know that summation ei x1i is equal to 0 and summation ei x2i is also equal to 0. So this identity becomes summation ei square is equal to summation ei yi. Now dear students, we know that this ei is again equal to y minus y hat, and putting the value of y hat again, we get summation y into y minus b1 hat x1 minus b2 hat x2. This is the value of small y hat, and multiplying y with the whole equation, we get summation y square minus b1 hat summation x1y minus b2 hat summation x2y. Putting the value of this summation ei square in this previous equation for R square, we get summation R square as summation y square minus summation y square minus b1 hat summation x1y minus b2 hat summation x2y. By multiplying this with the whole and simplifying the equation, we can get the formula for the R square y on x1 x2 as b1 hat summation x1y plus b2 hat summation x2y over summation y square. This is the formula for r square. The value of r square lies between 0 and 1, and the higher the value of r square, the greater the variation in y explained by x1 and x2. For example, we have the if the suppose the value of let's say let me insert text box. If this capital R square, if capital R square is 0.90, it means that 90% variation in the dependent variable y let me do the settings. 90% variation in the dependent variable y is due to the independent variables x1 and x2. So, dear students, R square shows the percentage variation in the dependent variable y, which is caused by the independent variable x1 and x2. If r square is equal to 0.9, it means 90% variation in the dependent variable is due to the independent variable x1 and x2. Similarly, we can generalize the simple multiple regression line to the n observations, and we can also extend the number of the variables to k. So if we have n observation in which a linear relation exists between y and k minus 1 explanatory variables, we include n observations of y and k minus 1 explanatory variables, means x1, x2, x3 up to xk. Then we can write the equation for extended equation, general equation, as yi is equal to b1 plus b2 x2i. I means for this y1, b3 x3i means x3 for this dependent variable, x4 b4 x4i, and so on till bk xki. Xki means xk observation independent variable for the observation y. If we extend it to n observations of y, we can write separate equations for y1, y2 till yn. We can write it in their equation matrix form as well. This matrix shows the matrix of the dependent variable from y to n. This shows the equations, systematic part of the equations with independent variables and the betas, and the last one part of the matrix shows the matrix of the error terms. Similarly, if we can extend it, we can write this equation in multiplication form, because if we multiply these two matrices through the matrix rules, we will get the same equations again. After introducing the generalized form of the regression, multiple regression, we can also generalize the formula of the R square. And it is not difficult to generalize it, because we already know that in case of one variable, we have R square as b1 summation x1 y by summation y square, or if you remember, you have another formula, summation xy divided by summation x1 square summation x2 square. You had used calculated in the chapter correlation, theory of correlation. You can calculate the R square with that, or you can also calculate with the formula v1 head summation x1y by summation y square. Similarly, if the variables are increased to 2, we derive this formula that r square will be equal to b1 summation x1y plus b2 head summation x2y by summation y square. If we extend it to n variables, then the formula also becomes generalized, and the formula number 3 in this slide, which you see, is r square y y x1 x2 x2k b1 head summation x1y plus b2 head summation x2y up to bk head summation xky by summation y square is actually a generalized formula. Dear students, after calculating the coefficient of multiple determination and finding the estimates of parameters for b1, b0 and b2, the next important topic is tests of significance for multiple regression estimates. For tests for significance for b0, b1 and b2 head, if you remember, you had the evaluation criteria in the methodology of econometrics, and one of the criteria was the evaluation of estimates, which consisted of criteria, economic criteria, statistical criteria and econometric criteria. And we said that in the econometric statistical criteria, we use different types of the tests. Some of the tests which have been already discussed. In case of simple linear regression model, we will give attached to those tests. The first test is the standard error test. We can conduct the standard error test for the 3 parameters b0, b1 head and b2 head. It starts with the null hypothesis. We write the general null hypothesis h0 beta I is equal to 0 against its alternative h1 beta I is not equal to 0. So the first h0 beta I is equal to 0 means that the estimates of the square estimate b0 and b1 are not significant, while the its alternative beta 0 beta I is not equal to 0 means that the estimate beta 0 beta 1 are significant. If the standard error of beta I hat is less than beta I hat by 2, remember, if the standard error of beta I hat is less than beta I hat by 2, it will mean that we reject the h0 and conclude that the least accept the h1 and conclude that the estimate is statistically significant. If the standard error of beta I hat is greater than beta I hat by 2, it will mean that the estimate of the parameter is we accept the h0 and the estimate of parameter is insignificant. For example, if you take the example of b0 hat, if we take the example of b0 hat, if the standard error of b0 hat is less than beta 0 hat by 2, it means that we reject h0 and conclude that beta 0 hat is significant. Similarly, we have other tests, t-test and z-test as well. For both the tests, we have a 6-step procedure. First, we state the null hypothesis denoted by h0, h0 beta I is equal to 0 against the alternative h1 beta I hat is not equal to 0. The next step is the level of significance. Here we fix the level of significance, how much percent we are sure, percentage of surety, the probability of surety, 0.01, 0.05, 0.1. These are different levels of significance which are used. Test statistic in step number 3, we specify the formula. If you are using t-test, then you write the formula for t-test, and if you are using z-test, then we write here the formula for z-test. Number 4 is critical region. In case of the critical region, we find the critical region in case of the z table through the z table, while in case of the t distribution, in case of the t-test, we use the t table. You can find the tables in any book of statistics or econometrics. In the step number 5, we calculate the values of the z and t with the help of the data and the formulas given in the step number 3. The last step is the conclusion. In this step, we decide on the basis of step number 4 and 5 the calculations of the calculated z and tabulated z. We compare the values of the tabulated z and t with the values of the calculated z and t. If the calculated z is greater than the critical value, it means that it lies in the critical region, and we reject the h naught of non-significance and conclude that it is significant. We will discuss this in the coming next example on the next slide. You will understand it better. Students, it is an example. This example is very important. If you understand this example, in this example all the concepts of the multiple regression have been covered. So the example is fit a multiple regression model, this one, given the following data, and also find the coefficient of multiple determination, means R square, the variances for the B0, B1, B2, and conduct test of significance. So let me solve it. Dear students, in the solution, first of all we write the estimated regression line. So this is the estimated regression line. B0, B1, B2 hat, you have to estimate it. These are the formulas we already discussed in the previous slides, the formula for R square. So we construct the table according to these variables. Similarly, for the variance of B1 hat, we have sigma square u into summation x2 square divided by summation x1 square, x2 square minus summation x1, x2 whole square. Similarly, variance of beta 2 hat can be estimated with this formula, and variance of B0 hat is estimated with this formula. We see here that we have a new term sigma square u here, and we will calculate this term as well. So the table, which is constructed on the basis of the formulas given in slide 19 and slide 20, the table which is already discussed, this is the table which is discussed at the beginning of this lecture. So from these values, we put these values in a formula for the B0, B1, B2 hat. We get the values of B1 hat, B0 hat, and B2 hat, and we discussed also this in the previous example. The next is to calculate the R square, which is B1 summation x1y plus B2 hat summation x2y by summation y square. So B1 hat, the value of B1 hat is minus 7.1889 into summation x1y is minus 300 plus B2 hat is 0.0143 into summation x2y. You can get summation x2y. This is 65,000 divided by summation y square, which you see in this table is 3,450. This is 450. So by simplification, by solving these calculations, we get the value of the R square, which is 0.894, which means that 89.4% variation in the demand is brought about by the independent variable income and price in this case. Now for the calculation of the variances, we need sigma square u, which is equal to summation ei square by n minus k. So we can calculate the summation ei square in the table as well, but that will be a lengthy process. So we use another formula which is derived from the formula of R square. Summation ei square is equal to y square, summation y square into 1 minus R square. We already calculated summation y square, so put the value of summation y square, and we have the value of the R square as 0.89. We put also that value here, and we do calculate summation ei square, which is 365.7. Then put it in the formula for sigma square u. We get sigma square u as 52.24. And if you put them in the with formulas for the variances discussed in this slide, we get the estimates of variances as 6.53, 0.0001, and 553.69. So from the variances, it is easy to calculate the standard errors. So this is the standard error of beta 1 hat, the standard error of beta 2 hat, and standard error of beta 0 hat. We can write the summary, which is a standard format of writing the summary of results. You can get it in some of the software as well. This is the estimated y, b0, b1 hat and b2 hat. The standard error which you see below the b0 hat is the standard of beta 0 hat. This is the standard error of beta 2 hat. This is the standard error of beta 2 hat. Beta 0, beta 1, beta 2. This has been the t statistic calculated for the beta 0 hat, beta 1 hat and beta 2 hat on the basis of the given data. So and this is R square calculated, and this is the t statistic at 0.05 level of significance in the given in the t table. So this is calculated t. This is calculated t for b1. This is calculated t for b1. So we compare the calculated t's with the critical value, and we can decide on the basis of these whether the estimates are significant or not. So first we come for the estimate of beta 0 hat. The t value calculated for it is 4.75. And the tabulated value is in the critical region is 2.36. So the calculated value is greater than the tabulated value, which means that this value lies in the critical region. So we reject H0 and conclude that beta 0 hat is significant. Similarly, if we check the t value for the beta 2 hat, it is minus 2.8, which is also lies in the critical region if we compare it with the this critical value. So we conclude that beta 1 hat is also significant. The value of beta 2, the value of the t calculated for the beta 2 is 1.28, which is less than the critical region 2.63. So it lies in the acceptance region, and we accept the hypothesis that beta 2 hat is not statistically significant. So dear students, make a practice of these questions, and hopefully you will come to know in easy way what is multiple regression and what are the terms relevant to the multiple regression. Thank you very much. You can the material in this book lecture has been taken from Korshiani's 1973 and D.M. Gujarati book Basic Econometrics. So for the detail you can give reading to these two books. Thank you.